Alright, in this video we'll be going through the 2022 Mechanics Exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video and see how I go about getting the answer. Alright, so some children are playing on a roundabout. Riley pushes the roundabout and gets it spinning at a constant angular velocity. It makes one revolution every 1.23 seconds. Show that the angular velocity of the roundabout is 5.11 radians per second. Alright, so we know that our angular velocity, omega, is equal to 2 pi all over the period. We can see that it makes one revolution every 1.23 seconds, and so 1.23 seconds is the period, and so 2 pi all over 1.23. This gives an angular velocity of 5.108, and therefore that's the same as 5.11 radians per second. There we go. So Riley stops pushing, and then 30 seconds later the roundabout has slowed down so that it takes 2.4 seconds to make one revolution now. The roundabout can be approximated as a spinning disc with a rotational inertia of 57.6 kg meters squared. Determine the angular deceleration of the roundabout as it slows down, and calculate the average frictional torque acting on the roundabout as it slows down. Alright, so we know our initial angular velocity was 5.11, so we can write down our initial angular velocity is 5.11 radians per second, okay? Now our final angular velocity can be found the same way our initial was found, where we have 2 pi all over our period, where in this case our period is now 2.4 seconds, so 2 pi all over 2.04, and that gives us a final angular velocity of 3.08 radians per second. Now this is a rounded version of the number, so make sure when you do your calculations you use the unrounded version. Now we want to find the average angular deceleration, and so the average angular deceleration is the change in omega all over the change in time. So the change in angular velocity over the change in time. And so change in omega is our omega finally minus our omega initially all over the change in time, which is 30 seconds in this case, right? So 30. So our omega finally is 3.08. And that's minus our omega initially, which is 5.11, all over 30 seconds, and that gives us an average deceleration of negative 0.068 radians per second per second. There we go. So now as we know that torque is equal to I alpha, right? And we just found our alpha right here, and we are given our rotational inertia, which is our I value, and so our torque is equal to 57.6 times negative 0.068, and this gives us a average torque of negative 3.898 Newton meters. There we go. For friends all ride on the roundabout in the position shown in the diagram. Explain using physics principles what the friends can do to make the roundabout speed up while staying on the platform. Exclude all external influences. Okay, so what these people can do is move towards the center of the disc, okay? Or the roundabout, if you will. And when they do that, more of the mass will be closer to the axis of rotation, right? So we know that this disc is spinning this way, and so the axis of rotation is in the middle. And so if all these people move towards the center, the mass is more concentrated towards the axis of rotation. And therefore, as I is directly proportional to mr squared, as more of the mass is closer to the axis of rotation, the effective radius is going to decrease, and therefore our rotational inertia is going to decrease, okay? Now, if you don't know what effective radius is, I go through it in my rotational motion videos in my mechanics playlist. And as angular momentum is equal to I omega, and also due to the fact that there are no external forces, our angular momentum is constant, okay? And so because this is constant, and our rotational inertia has decreased, our angular velocity must increase. And because our angular velocity has increased, the roundabout is going to spin faster, okay? And you can write that in words. Matilda wants to run and jump onto the initially stationary roundabout, holding onto poles at A or B to make it spin as fast as possible. She tries different jumps onto the roundabout. Assuming that she always jumps at the same speed, explain which jump A or B will make the roundabout spin faster. So the answer in this case is jump A. So when she jumps at position A, that's where the roundabout is going to spin faster, okay? The reason for that is because torque is equal to force times distance, where in this case our distance is our radius, okay? So torque is equal to force times our radius. Now this equation is slightly misleading. The full equation is torque is equal to F sine theta times our radius or distance, okay? Now this sine theta is important because it tells us that the angle at which the force is applied matters. So let's say, for example, we have a pole, okay, and this pole is on a pivot, okay, and so this pole is able to rotate 360 degrees. If we would apply a force over here, we know that this pole is going to go this way in a circle, okay? However, if we apply a force this way, we intuitively know that it's still going to rotate, but it's going to rotate slower. Why is that? Because only the force that is perpendicular to this lever is going to cause rotation. So perpendicular meaning at right angles, okay? And we know that if we have a force coming like this, we can split this force up into horizontal and vertical components. And so the only component of this force that's going to cause rotation is this component right here, okay? So now why is sine theta used? Well, if we think about it, if a force is directly at right angles to this lever arm, meaning we have a right angle right here, sine 90 degrees is equal to 1, okay? And so therefore, it's F times 1 times R, which is F times R, okay? So the sine component effectively just goes away. However, if the force is coming in like this, and let's say this is 30 degrees, okay? And so we would have to do sine 30 degrees, which is equal to half. And so we would have half our force times our radius will give us our torque, okay? So now, taking that theory and applying it to here, we can see that this disk is effectively the same as our lever arm, okay? If we apply a force here, we know that this point is going to rotate across, okay? And so we can draw our lever arm right here. We can see that the force applied at A is directly perpendicular, and so sine is equal to 90 degrees, and therefore that's 1, okay? However, at B, if we draw our lever right there, we are applying a force like this, and so therefore there's an angle right here, and that angle is obviously greater than 90 degrees, and if the angle theta is greater than 90 degrees, then sine theta is going to be less than 1, and so our perpendicular force at B is going to be less than A. And so, if our force is less at B than at A, our torque at B is going to be less than A. And so A will apply the most torque, okay? So now that we established A applies the most torque, and so therefore as A applies the most torque, as torque is equal to I alpha, if A applies a larger torque, therefore A will also result in a larger angular acceleration, and therefore it would rotate faster, okay? And you can write that in some words. Matilda lets go of the pole and slips off the roundabout. Discuss the possible effects on the speed of the roundabout. Assume there is negligible friction between Matilda and the roundabout. Now, the clue of this question is that Matilda and the roundabout have no friction between each other. And so what that means is that there is no force between Matilda's foot and the roundabout. So therefore, as Matilda does not apply a force to the roundabout, that means she can't apply a torque to the roundabout, right? Because we know that torque is equal to force times distance. If our force is equal to 0, that means our torque must be equal to 0, okay? And so because she doesn't apply a torque as she's slipping off the roundabout, this means that the angular velocity of the roundabout does not change. Now, so that is one way to answer the question. The other way we can answer this question is that the angular momentum of the system is equal to the angular momentum of the roundabout plus the angular momentum of Matilda. Now, as you can see from this equation, Matilda's angular momentum has no effect on the angular momentum of the roundabout. And so when Matilda slips off the roundabout, she does not remove angular momentum from the roundabout. And so therefore, the angular momentum of the roundabout does not change. And so therefore, as the angular momentum of the roundabout does not change, the velocity or angular velocity of the roundabout also does not change, okay? Comets and asteroids are loosely formed objects that can easily be broken up, especially when they collide. In this scenario, a 100 kg object with a velocity of 500 meters per second collides with a stationary 300 kg object, okay? Calculate the distance of the center of mass of the system from the 300 kg object when the objects are 4,000 meters apart. We know our equation for center of mass is x center of mass is equal to m1x1 plus m2x2 all over m1 plus m2. Now we are calculating the distance from our 300 kg mass, and so we can set this as our reference point, and let's say our 300 kg mass is equal to m2 and our 100 kg mass is equal to m1. As our reference point is the 300 kg mass, our x2 is going to be 0 meters, and our x1 is going to be 4,000 meters. Okay, now we can just simply plug in our numbers. M1 is 100 kgs times x1, which is 4,000, plus our 300 kg mass times x2, which is 0, all over 100 plus 300. And therefore, as we know, this cancels out. And so therefore, this gives us a center of mass of 1,000 meters. There we go. And so we know this is 1,000 meters from our 300 kg mass. So that probably is like right there, okay? Calculate the gravitational force between the two objects when their center of masses are 10 meters apart. Assume that the velocities of the center of mass are constant before the collision. So we know that F is equal to our gravitational constant times our big mass times our little mass all over radius squared, where our r is the distance between the two center of masses of the objects, okay? So what that means is if we have our small object here and our big object here, the distance between the center of masses is this distance right here. Now in this case, we are given the distance between the center of masses, however there are some questions where it only gives you the questions between the two surfaces of the masses, and we need to add the radius of each mass onto our distance, okay? That's just to be wary of. But in this case, we don't have to worry about that because we are given the distance between the two center of masses, okay? And so therefore, our gravitational constant is 6.67 times 10 to the negative 11 times our big mass, which we know is 300 kgs, times our little mass, which is 100 kgs, all over our radius squared, which is 10 squared. And this gives us a force of 2.001 times 10 to the negative 8 newtons, okay? So a very, very small force. And so this is a continuation of the previous question. Find the acceleration of the 100 kg object at the separation to determine whether the assumption that the velocities are constant before this collision is valid, okay? So as we know, our F is equal to ma, and therefore our acceleration is the force all over the mass. We found the force as 2.001 times 10 to the negative 8 newtons, and so we can plug that in, all over our mass, which we know is 100 kgs, because that's the one we're trying to find. And this gives 2.001 times 10 to the negative 10 meters per second. There we go. Now, determine whether the assumption that the velocities are constant before the collision is valid. Now, there are two ways to answer this. Either we can say that it is valid, or that it isn't valid. Both are marked as correct in the marking schedule, you just simply have to justify it. So the first option, we can say that the assumption is valid, and this is because 2.001 times 10 to the negative 10 meters per second, okay? That is very, very small, and so we can say that's basically the same as saying the acceleration is 0, and as we know, our acceleration is the change in velocity over time, and therefore our change in velocity is equal to acceleration times time, and if our acceleration is practically 0, or we can say approximately 0, therefore our change in velocity is also approximately 0, okay? And so we can say that the assumption is valid. On the other hand, we can also say that the assumption is invalid. This is because we can argue that there is an acceleration. Even if the acceleration is very, very small, there is still an acceleration, and so therefore we can say that the assumption is invalid because the acceleration is not 0, and therefore as acceleration is the change in velocity over time, and the change in velocity is the acceleration times time, as the acceleration is not 0. Therefore, there must be some sort of change in velocity, even if it's very, very small, and so therefore the assumption is invalid. Again, both are marked as correct in the marking schedule, you just have to justify it as so, okay? So if you justify it correctly, then you'll get the question right. The objects collide with no external forces and form two rocks, A and B, each with a mass of 200 kgs. These move away from each other as shown in the diagram in directions 20 degrees either side of their initial direction of impact, okay? Show that the size of the momentum of rocks A and B are the same even though they're in different directions. You may use the space below for some vector diagrams, okay? So as all the way up here, we can see that the momentum initially, the direction is purely to the right because only the 100 kg mass is moving. The 300 kg mass is stationary, and so the 300 kg mass has no momentum. And so the only object in the system that is carrying momentum is the 100 kg mass, and that is moving to the right, and therefore the momentum is always to the right. So therefore, initially, we can say that the momentum is like so. Now afterwards, we can see that the momentum of A goes up in this direction at 20 degrees, and so we can say it's like that. And we can see that the momentum of B comes down this way, also at an angle of 20 degrees, and so we can say it's like so. And we know this because as momentum is conserved, the initial momentum in the vertical direction, so y for vertical, must be equal to the momentum finally also in the vertical direction, okay? And so initially we can see that the momentum has no vertical component, it's purely horizontal. And so therefore finally we can see that our object A, and this is our object B, right? They're vectors. We can see that A comes up, and therefore B must have the exact same magnitude just in the opposite direction to cancel out that vertical component of A, therefore keeping this true. Also, the initial momentum in the horizontal direction must be equal to the final momentum in the horizontal direction, and as you can see, we close that loop in the horizontal direction as well, okay? Calculate the speed of rocks A and B. You may use the space below to draw vector diagrams, okay? Begin your answer by calculating the total momentum before the collision, okay? So, as stated before, we have our vector diagrams like so, and like so, and like so, okay? So this is our A, this is our B, and this is our initial, okay? Now, our momentum initially, as I said before, was purely the 100 kg rock, okay? So purely the 100 kg rock. The 100 kg rock is moving at 500 meters per second. And so as we know, our momentum is mass times velocity, and so therefore that's 100 times 500, and that is equal to 50,000 kg meters per second, okay? And as stated in the previous question, this initial momentum is purely horizontal, and so therefore the initial momentum must be equal to the horizontal component of A plus the horizontal component of B, okay? So as we know, if we take our momentum of A, we can split that off into horizontal and vertical components, and so this is PAX and this is PAY, and we can do the same for B as well, right? This is PBX, this is PBY, and this is the momentum of B, okay? Momentum and then momentum, like so, okay? And so our initial momentum is equal to the horizontal component of A plus the horizontal component of B, okay? And so therefore, our initial momentum is equal to the mass of A times the velocity of A cos 20 degrees, okay? Remember, there was a 20-degree angle here, okay? Plus the mass of B times the velocity of B cos 20 degrees, okay? Now, because we know each fragment has the exact same mass of 200 kgs, and they fly off with the exact same angle of 20 degrees, we know that they must fly off with the exact same velocity, okay? The exact same magnitude and velocity. The direction is going to be different, but the magnitude is going to be same. And so we can say that VA is going to be equal to VB. And we also know that the mass of A is equal to the mass of B. And so our momentum initially is equal to 2 times mv cos 20 degrees, okay? And so therefore, 50,000 is equal to 2 times 200, right? Because that's the mass, times our velocity, which is what we're trying to find, times cos 20 degrees. And so therefore, 50,000 all over 2 times 200 times cos 20 degrees is equal to our velocity, and this gives us a velocity of 133 meters per second. There we go. Some space explorers on Mars went to check that their electronic timers are functioning correctly. They make a simple pendulum using a large rock of mass 2.3 kgs, which is tied to a wire. The distance from the center of mass of the rocks to the fixing point is 1.83 meters. On Mars, the gravitational field strength is 3.72 newtons per kg. Show that the time period of the pendulum is 4.41 seconds, okay? So we know that for a pendulum, our period is equal to 2 pi square root L over G, okay? Where L is the length of the pendulum, and G is our acceleration due to gravity. One thing that might trip you up is that you don't quite understand what is gravitational field strength. That is fine. However, we can do some dimensional analysis to find out what that is. Now, we know that the unit for acceleration due to gravity is equal to meters per second, right? Now, what you may not know is that newtons per kg is equal to meters per second in terms of their dimensions, okay? Now, I'll show you how you can figure that out. We know that force is equal to ma. We know that the unit for force is newtons, the unit for mass is kg, and the unit for acceleration is meters per second. And therefore, we can say that the newton is equivalent to kg meters per second. So this is actually a valid unit for force. If you ever forget what the unit for force is and you can't remember that it's newtons, you can put kg meters per second and you'll get the full marks, okay? So now, subbing this in for this, we get kg, meters per second, all over kg is equal to meters per second. And sure enough, we can see that the kgs cancel out, and we get meters per second is equal to meters per second, okay? If you want more on this, you can check out the scholarship playlist, I think, and it's one of the first videos where I go through dimensional analysis, okay? You can tell it's one of my first videos. It's the quality is not as great, but whatever. So therefore, we know that this is actually saying that this is the acceleration due to gravity on Mars, okay? And so now we've got all our information. We can say the period is equal to 2 pi square root the length, which is 1.83, all over 3.72, and that gives us a period of 4.407, which we can say is 4.41 seconds. There we go. They oscillate the pendulum by releasing the pendulum bob 0.3 meters away from its rest position. At the same moment, they start the timer. Determine the position of the pendulum bob from its release point 2 seconds after it is released. So because it's released 0.3 meters away, we know that's our amplitude, and so we are starting from the extremes. And so the radius of our reference circle is 0.3 meters, okay? We know our omega is equal to 2 pi all over t. We already know our period because that's 4.41 seconds, which we just found. So that's 2 pi all over 4.41. And that gives us a angular velocity of 1.42 radians per second, okay? And therefore, right off the bat, we can find our theta is equal to omega t. Our t value is 2 seconds because that's what we're trying to find right after 2 seconds. And so our theta is equal to 1.42 times 2, and therefore our theta is 2.85 radians. And as we are starting at the extremes, we can find our displacement is equal to our amplitude cos theta, okay? And so therefore our displacement after 2 seconds is 0.3 cos 2.85, okay? And this gives us a displacement of negative 0.287 meters, okay? Now, if we look at our reference circle, we know our period is 4.41, and so it takes 4.41 seconds for it to come this way and then all the way back. And so most likely, we are somewhere over here, okay? We're somewhere over there. And so we know that this distance right here is 0.3 meters, okay? And what we just found is that this distance right here is 0.287 meters, okay? Now, obviously, this is negative, and what that negative is basically saying, if this way is positive, then this way will be negative, okay? Negative and then positive. And so the distance from our release point is going to be 0.3 plus 0.287, and that's equal to 0.587 meters, okay? There we go. The amplitude of the pendulum decreases from 0.3 meters to 0.2 meters. Explain why the period of the pendulum remains unchanged. So there are two ways to answer this. The first way is to say that our period is equal to 2 pi square root L over G. And so as you can see from this equation, our amplitude has no bearing on the period. And so we can say from here, our amplitude has no effect on period. Okay? Sweet. The second way is using the definition of simple harmonic motion. We know that in simple harmonic motion, the restoring acceleration, which is the acceleration that brings the pendulum back to its equilibrium center position, is proportional to the displacement. And so if the displacement is smaller, this acceleration is going to be smaller, and therefore the pendulum is going to move slower. And so therefore, as the pendulum is moving slower, the pendulum period remains unchanged. Okay? So two ways. Me personally, I prefer this way because it's easier to explain, but this way is still completely valid. Calculate the total energy loss when the amplitude decreases from 0.3 to 0.2 meters. Begin your answer by calculating the maximum velocity of the bob from the initial and final amplitude. So if we look at our pendulum, in this case, when the pendulum is moving, it's going to have max velocity and minimum EK. However, when the pendulum is at max displacement, it's going to be momentarily stationary, so therefore the velocity is 0, and so therefore the EK is equal to 0, but it's going to have the most amount of EP because it's at its highest point, right? This is delta H, okay? And as you can see here, delta H is equal to 0. So in this case, EP is 0, but EK is max. But in this case, EK is 0, but EP is max. But due to energy conservation, we know that this max EK must be equal to this max EP. So if we want to calculate the energy loss, we can just use EK, okay? Because we have no information on this delta H, we have no idea how high it rises, okay? So using EK is the only viable option. So we know that EK is equal to half mv squared. We are given the mass of the bulb that's given in the start of the question. However, now we just need to find the velocity. If when the pendulum is at the bottom, this is when EK is max, we can therefore determine that is when we have max velocity, okay? Vmax in simple harmonic motion is equal to our amplitude times our angular velocity. If you don't know where that comes from, watch my reference circle video. I go through it in that video, okay? But our Vmax is equal to A omega, okay? And so therefore, for our initial case, where we had initially a amplitude of 0.3, we can say that 0.3 times our angular velocity, which we calculated before, right here as 1.42, okay? 1.42, and this gives us a Vmax of 0.426, and therefore, as EK is equal to half mv squared, as our mass is equal to 2.3 kgs, right? That is given right here. We can say our EK is equal to half times 2.3 times 0.426 squared, and that's equal to 0.2086974 joules, okay? So that's our initial case. Our final case, we can say that Vmax is equal to A omega again, where our amplitude this time is 0.2 meters, right, over here, times our angular velocity, which is 1.42 meters. Now remember, our angular velocity does not change because our angular velocity is 2 pi all over our period. And we established in the previous question that our period does not change when we reduce the amplitude, okay? So therefore, our angular velocity does not change. So this gives a Vmax of 0.284 meters per second, okay? And so the EK is equal to half mv squared, half times 2.3 times 0.284 squared. This gives 0.0927544 joules, okay? And so to find the difference, right, we're trying to find the energy loss, so that's the difference in energy. That's 0.2086974 minus 0.0927544, and this gives an energy loss of 0.116 joules. There we go. Now the marking schedule gives 0.118 joules, however, I just think this is a discrepancy in rounding, okay? Basically the same answer. And we're done. See ya.